so this is the outline of chapter 21 about the Coulomb's law. Okay, so the outline is very simple. So it only talks about the Coulomb's law itself, and then the charge is quantized, charge is conserved. Okay. Okay, so yeah, so first, okay, so this is a very simple experiment. Okay, so the title is Magic ? Okay, so it says yeah, the two glass rods were each rubbed with a steel cloth, and one was suspended by thread. Okay, and when they are close to each other, they repel each other. Yeah, of course you don't need to memorize this. I don't. I'll see in the exam. Okay. Anyway, so so the idea here is like yeah, just look at this part. Yeah, you have two glass rods. Okay, if you just put two glass rods together, so nothing happened. But you try to use a steel cloth to rub one of the glass rod, and then the other one hanging here. Okay, so it is free to rotate. Okay, so in this case, after you rubbing the glass, one of the glass rod, and then put it closer to this one. Okay, so they will repel each other. They will repel each other. So this is the first phenomenon. Okay, and then the second one is like yeah. So here you still have this glass rod, but here we have another plastic rod rather than another glass rod, and then you rub it with fur, and then when brought close to the glass rod, they attract each other. Okay, they attract each other, or maybe the plastic rod attract the glass rod. Okay, so according to the title, is it a magic? Is it a magic? Okay, so as a physician, they see some phenomenon, they will try to explain it, and then by this way they try to build up the theory. Okay, and then try to hope this theory can explain more and more phenomenon, as many as possible. Okay, so here they introduce a concept called the electric charge. So the idea is like for the two glass rods, after you rubbing it with the steel cloth, okay, so they all have positive charge on it. Okay, so when you place them close together, then they have same charge. Okay, same charge, so they will expel each other. Okay, and then for the bottom one, yeah, so still here we have a positive charge. But for the plastic one, after rubbing it with the fur, it has negative charge. So they have opposite charge, so they attract each other. Okay, so don't ask why the glass one has the positive charge and the plastic one has the negative charge. It relates to the chemical structure. So I'm not familiar with it. But yeah, so it's just a physical experiment to just introduce the idea of the charge. We have positive charge and negative charge. Okay, so as a highlight, it says particle with the same sign of electrical charge repel each other, and the particles with opposite signs attract each other. Okay, so in Chinese it's called 同性相聚相似异性相吸 Okay, anyway. Okay, so based on this, yeah, they try to separate the material based on the conductivity into roughly four categories. So the first one is called the conductor. Okay, probably you know this during the primary school. Conductor, insulator. Okay, so conductor are material with a significant number of electrons are free to move. example include metals. Okay, so probably the element on the left part of the periodic table. Yeah, so the conductor, the main point is with electron. If with electrons that are free to move. Okay, which means the conductor has free electrons. Okay, so and then the other one is the insulator or non-conductor. So the charged particle in the non-conductor or insulator are not free to move. Example include rubber, plastic, glass. Okay, so which means these are not free electron. Okay, are not free electron. So the charge will stay there after you rub with a steel cloth or a fur. Okay, so the charge stay there. Maybe it will leak very, very slowly, but in a short while the electron are just stay there. It cannot move to the other part of the rod. Okay, so that's the point here. And the third part is the semiconductor. Okay, 半导体. Okay, so probably in the middle part around 4A column in the periodic table. So a material that are intermediate between conductors and insulators. Example include silicon, germanium in computer chips. Okay, probably, yeah. So semiconductor, the introduction of the semiconductor are just up to this point. Yeah, because if you really need to learn more about the semiconductor, it will be some hardcore lecture in the physics or in the ECE. Okay, they will have several courses about this crazy element. Okay, because semiconductor are kind of non-linear. Okay, non-linear. Okay, non-linear is a very important word during your engineering study. Linear and non-linear. Linear. 线性, 非线性. Okay, so actually most of the thing you learn in the bachelor study will be linear. Okay, including the constant coefficient ODE is describing a linear system. Okay, and then so most of the linear system will be solvable. There are plenty of theory to solve this kind of problems. But for non-linear element, non-linear system, it will be really, really complicated. Sometimes it is not solvable by hand calculation. You can only use some numerical method to solve the non-linear system. Yeah. And actually the semiconductor, the characteristics of the semiconductor are quite non-linear. Okay, so it will be really, really complicated. But actually we can use it to construct something like the transistor, which can be used for some amplification or maybe used for some logic circuit. Yeah, so the transistor or more lengthy word is called the MOSFET. Okay, MOSFET. MOSFET is actually a short form, metal oxide semiconductor field effect transistor. Okay, or sometimes it is shortened as the MOS. And there will be two types of MOS called the PMOS and NMOS. Okay, so using both PMOS and NMOS as the logic circuit, we call it the CMOS. Okay, so probably if you're familiar, if you like to construct your computer by yourself, okay, you may have seen the CMOS in the BIOS page. Okay, so called the CMOS, complementary metal oxide semiconductor. Yeah, so those are complicated stuff. Okay, about the solid state physics, 固态物理. Okay. Anyway, I will just stop here for this course. And then also the superconductor is another one. We just stop here. Yeah, because I know nothing else about the superconductor. Yeah, about the 超导体. Okay, superconductor are something like it has a perfect that are perfect conductors, which means it has zero resistance in the superconductor material. Yeah, and actually you need actually during its invention, okay, you need a really low temperature to have the phenomenon of superconductor, like 4 Kelvin, or maybe less than 4 Kelvin. 4 Kelvin, okay, which means it is less than negative 269 degrees Celsius, okay. So it is a really low temperature. Maybe you need to use some pressure to make it happen. Okay, yeah, because you know that PV equals nRT during the chemistry class. Yeah. So anyway, superconductor is like that. Okay. So yeah, at least at the very beginning they try to they need the liquid helium to make the superconductor happen, and later on the guy work on the material, try to find some material that can have a superconductor with a higher and higher temperature. Yeah, but yeah, I don't talk too much about that. Yeah, so anyway, just go back to here because this is electromagnetism. We actually focus only on the conductor and insulator in this course. Yeah, so actually the charged particles, yeah, we have, so in the high school chemistry class, you probably learn the atom structure, So for an atom, it has, I mean for an element, it has a nucleus and also some electrons. Okay, so it has some electrons. Okay, with negative charge, and then it also have a nucleus. The nucleus consists of protons and neutrons. The protons have a positive charge, and the neutrons have no charge. Okay, or neutral. Okay, charge neutral. So anyway, during the chemistry class, you should have known that for an atom, it has a purely no charge. So the negative charge from the electrons and the positive charge from the proton just perfectly cancel each other with a perfectly same amount. Okay, so yeah. And actually for the metal, for the conductor, the free electron is of course due to the electrons. And actually for the insulator, it can have something called an induced charge. Induced charge in Chinese is called 感应电荷. Okay, induced charge. 感应. Okay, so like this. Okay, so here it says a neutral copper rod is electrically isolated from its surrounding by being suspended on a non-conducting thread. It means that this copper rod is neutral. Neutral in charge. Okay, which means a perfectly zero charge, perfectly zero net charge. Either end of the copper rod will attract by a charged rod. Here, conduction electrons in the copper rod are repelled to the far end of the rod by the negative charge of the plastic rod. Okay, so just now we try to have a plastic rod rod by a third so that it has a negative charge. Negative charge. So when we place it to a copper rod, which is charge neutral. Okay, the whole rod is neutrally charged. Okay, with zero net charge, but actually they will attract each other. Okay, they will attract each other. Yeah, because this is a metal. This is a conductor. Okay, it has 3 electrons. Different from the glass rod. The glass rod won't have 3 electrons. This one, it has 3 electrons, which means that the 3 electrons are also negative charge. The electron and this negative charge will repel each other. So this charge tries to go to the other end. Okay, so which means that it is an induced charge. So even though the whole rod with 0 net charge, but this end we have positive charge, and then the other end have induced negative charge. So and then they add up to the 0 still because no charge can enter or coming out from this copper rod. Okay, in that case, as all the 3 electrons go to the other side, this side will be positive, and then positive negative will attract each other. Okay, so this is called an induced charge. Okay, so after talking about some phenomenons, okay, so we come down to some equations. Okay, so first is a definition for the charge. Okay, although this definition is quite strange. Yeah, because usually you try to define something, you try to say, oh, this one is equal to something else. Okay, but this one is different. Okay, so for the charge is here, charge is Q. Okay, the definition will be like, yeah, it's like the definition of the current rather than, okay, so this is the current. I is the current. Okay, so this is the charge. This is the charge. Okay, so you may ask, why not using the Q equals something else? Okay, yeah, actually you can do it like this. You can do it like Q equals integration of I dt. Yeah, something like that. Of course, you can give it some lower and upper bound as a definite integral. Yeah. Anyway, so they try to avoid this integration. Okay, just give it this I equals dq dt. So just try to take the derivative of the charge with respect to time will be the current. Okay, and yeah, actually I need to emphasize that the SI unit is really important for the physics and for the engineering. Yeah, so you need to memorize all the SI unit. You need to memorize all the SI unit. Yeah, in the quiz or exam, every incorrect SI unit will count for 1 point. Okay, so pay attention to all the SI unit during the lecture. Okay, so first of all, the SI unit for the charge, is Coulomb. Okay, yeah, the SI unit for the charge is Coulomb. Okay, in short form is C, capital C. And the SI unit for the current is ampere. Okay, this one is ampere. Okay, this one is for that one. So yeah. So but here it says 1C is like 1A times 1S. Okay, so yeah, based on this one. Okay, based on this one. Okay, you can try to consider this derivative is like a division. Okay, so which means that the SI unit here, I will be 1A. The 1A will be equal to 1C, and then for the SI unit for the time is of course second. So so with this one, if you can remember, this is ampere, this is this is Coulomb. You can quickly know that 1A is actually 1C over 1S. Okay, something like this. Okay, so yeah, so that's the point here. Or if you just move 1S to the left side, 1C is 1A times 1S, which is this one. Okay, so this is the definition of the charge up till now. Okay, so here we talk about the Coulomb's law. Okay, the Coulomb's law. So the Coulomb's law describes the electrostatic force or electric force. Okay, between two charged particles. Between two charged particles. Okay, so the first keyword is two charged particles. Okay, as long as you have two charged particles, you can apply this. If you have more than it will be more complicated. You need to solve it carefully. Yeah, of course, these two charged particles include two keywords. One is two, one is charge. Okay, you need to have two charge. Okay, if one of it is zero charge, then there will be no electrostatic force. Okay, so here it tries to define the charged particle have charge Q1 and Q2. Okay, Q1 and Q2 are separated by distance R. Are set at rest. Okay, are set at rest. Okay, this is the assumption. This is the assumption. You assume they are at rest. They didn't move at all. Okay, and then these forces will be applied at that moment. Okay, a fraction of time later, then the force will already change. So because if according to Newton's second law of motion, you know, as long as a force acting on an object, then there will be F equals ma, and then it will start to accelerate and then try to move. Okay, so the force only apply to that moment only. Okay, so this is why we call it the electrostatics. 静电力或者是叫做静电学这四章叫做静电学。Okay, electrostatics, and then the force is called the electrostatic force. Okay, because it's just applied at that single moment. Yeah, so they are relative to each other. Then the magnitude of the force acting on each due to the other is given by this formula. So this is called the Coulomb's law. You should have learned it in high school physics. Yeah, but this is a vector form. Okay, this is a vector form. Okay, so let me try to explain how this coordinate system work. Okay, this is called you can call it the spherical coordinate. Okay, spherical coordinate. Okay, 球坐标啊，球坐标。球坐标。Okay, spherical coordinate. So it means that here you have two charge. Okay, we just assume they both of them are a positive charge. Here, and then this is Q1, this is Q2, and yeah, so that you have F acting on both of them. This one applies to both of them. Although in this graph you only draw F here, actually this F is also here. Okay, and then here so this is a vector. Okay, this is a vector, and then on the right side should also be a vector. Okay, so this one is also a vector. Yeah, but the symbol are a little bit different. Okay, you see, this is an arrow. Okay, this is called a head. This is called a head. This is a head. This is vector F. This is our head. Okay, so this is usually this head also referred to a unit vector. Unit vector. 单位向量。Okay, so of course in xy coordinate or Cartesian coordinate, okay, the unit vector are easy to understand. Okay, the the x direction, okay, you have I hat, and then for the y direction you have j hat, and then for the z direction you have a k hat, something like that. It will be used for this the textbook. But for the spherical coordinate, the unit vector are different for different point. Okay, the point here is that if we consider the force acting on Q1 induced by Q2, okay, so our coordinate system, okay, let me erase it at this moment. Here, you will just count it starting from here, and then the out hat will be pointing to the right side, okay, pointing to the right side. You try to connect Q1, Q2 and Q1, and then try to extend, okay, and then this direction is the out hat for this one, for Q1 only, and then of course the length of our head is 1, okay, we will just note it by our head, take the absolute value will be the length or the norm of it will be 1, okay, so which means our head is a unit vector. Okay, so our head point to the right side, okay, so this is pretty much it. So as long as you know this one, you can understand the whole formula, which means that this is a vector, this is a vector, all of these are some scalars. Okay, so Q1, Q2 already defined here, R already defined. This is only the distance between them. And then the remaining part, 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught. Okay, so this is a very, very important constant, or a mix of constants. So the most important constant, one of the most important constant in electromagnetic sum is epsilon 0, okay, 8.85 times 10 to the negative 12, c squared per Newton meter square. Okay, of course I can't remember this SI unit. Actually, I will give you if you during the exam. Actually, I have already memorized this number. Yeah, because I teach this course every year. So yeah, so many of the concepts I already memorized the number. So 8.85 times 10 to negative 12 is important. Although in the first half of this semester, we seldom use it individually. Okay, usually we will try to use it as a whole, as 1 over 4 pi epsilon naught, as a big constant. And then in this textbook, we just denote it as k. Okay, where k is 8.99 times 10 to the 9th power. Of course, the SI unit is inverse of that one, yeah, because 1 does not have a unit, 4 pi does not have unit. So the unit of k and 1 over 4 pi epsilon naught, k and epsilon naught is just have an inverse SI unit. Okay, so how we understand it? So here, if both Q1 and Q2 are positive charge, which means that the direction of the force are the same as the direction of the unit vector. So which means that F points to the right side. Okay, just now I just mentioned the force acting on Q1. So here, when we consider Q2, the coordinate system is like this. We start from here, go to the Q2. So in this way, we have our head pointing to the opposite side. So this our head is only applied for Q2, okay, as this coordinate system. And then this our head is applied for Q1 in another spherical coordinate. Okay, so in that case, according to the same formula, Q1, Q2, R square, and also this K are all positive. So which means that F and R hat also point to the same direction, have the same polarity, so F points to this side. Okay, so which means that we can true. If both Q1, Q2 are positive, yeah, they will repel each other. They will repel each other with this one. Okay, so so here, so how about if one or two of them, two of the charges are not positive, are actually negative? So the electrostatic force vector acting on the charged particle due to a second charged particle is either directly towards the second particle or directly away from it. Okay, so yeah, so they either attract or repel. Okay, yeah, so maybe you feel that it is straightforward, but actually for the magnetic force, okay, this is not the same. Okay, so the direction of the force will be perpendicular, yeah, to the to that. Yeah, so here if both of the charges are negative, okay, so we try to plug in the same equation, although we use k here rather than 1 over 4 pi epsilon naught, although they refer to the same value. But at very least, this is positive. And here we assume for the case B, okay, Q1, Q2 are all negative. Okay, so Q1, Q2 are negative. So negative times negative is still positive. So this is positive, and then this is also positive. So which means that F is equal to a positive number times R hat. Okay, so which means this one and this one point to the same direction. And this is it. Okay, so for this one, still R hat point to the right side, this R hat point to the left side. So F is point to the right side for the right charge, and then F is point to the left side for the left charge. Okay, so this is it for this case. And the third case is if one of the charge is positive and the other one is negative. So you still you still plug in the same equation. Okay, K is positive. Suppose this is Q1, Q1 is positive, this is negative, this is also positive. R squared is also positive. Okay, so only one is negative, so which means that F is like a very positive number times R hat. Okay, so which means that F and R hat points to the opposite direction. So which means that still R hat, the definition of R hat does not change at any situation. Yeah, but F points to the opposite direction to the R hat. Okay, F points to the opposite direction to the R hat. So this says that if the polarity are opposite to each other, then the two charges will attract each other. Okay, we don't try to go into negative positive, yeah, because actually they are the same thing as case C. Okay, so but actually all the four combinations are all covered. Positive, positive, negative, negative, positive, negative, positive, negative, positive are the same. So in summary, same polarity repel each other, and then opposite polarity will attract each other. And actually, if you just care about the direction, okay, from the Coulomb's law, and then actually these parts, okay, actually these parts tells you the magnitude of the force, okay, the magnitude of the force. And of course this is a constant, okay, so it won't change in any case, as long as you keep it in a free space, okay, like in the air or in a vacuum, okay. If it is in another material, this is the other case. Yeah, but we'll talk about it later on. Okay, so the idea here is like Q1, Q2, and R are variable, which means that if Q1, Q2 increase, the force becomes larger. and R becomes, if R increase, F becomes smaller. Okay, so yeah. Okay, so just now I emphasized that the Coulomb's law is only applied for two charged particles. Only for two charged particles. Two. So if there are more than two charges, what will happen? What we need to do? So if multiple electrical forces act on a particle, the net force is the vector sum. Vector sum. Very annoying. Vector sum, not scalar sum of the individual forces. Okay, which means that if there are n charged particles, the net force acting on the charge number 1 will be like the force due to charge 2 acting on charge 1, due to charge 3 acting on force 1, all the way up to due to the charge n acting on charge 1. Okay, so there will be n minus 1 forces, and then you need to add them as a vector sum, which means that you need to decomposite the forces along x-axis, y-axis, and then x-axis component and y components individually. And then finally, it becomes the net force. Okay, so I suppose you should have facing this kind of calculation in high school physics. Not necessarily for the Coulomb's force, but maybe for some mechanical problems. Okay, so here we have another one called the shell theories. The shell theories. Okay, of course we will only talk about the theory itself here. We will not try to explain why it is correct. Okay, because we don't have the Gauss law yet. Okay, in chapter 23, when we talk about the Gauss law, we will come back to explain why these two theory is correct. So just now you just try to believe they are correct. Yeah. Okay, so the shell theories include two statements. Okay, two shell theories for the electrostatic force. For the first one, shell theory 1, okay, a charged particle outside a shell with charge uniformly distributed on its surface is attracted or repelled as if the shell's charge were concentrated as a particle at its center. Okay, let me try to draw a graph to explain this. So it means that if we have a sphere, okay, of course I can only do a circle rather than a sphere, but it should be 3D, okay? It means that if it is a perfect sphere, 这是一个完美的球体了, okay? And then, so in that case, if it has some charge, okay, can be either positive charge or negative charge. So I just draw it as a positive charge as an example, okay? For negative charge, it still works as it's, okay? Okay, so as much as the sphere is perfect, okay? 是一个完美的球体的话 okay, the charge density will be uniform, okay? Will be uniform, okay? Uniform. Okay, 均匀的 okay, will be uniform distributed along the surface, okay, as long as it is a conductor. I guess, okay, it doesn't really matter whether it is a conductor or insulator at this point. Okay, you just assume that, yeah, I guess it should be conductor. I guess it should be conductor. Yeah, because the charge will be uniformly distributed on this surface. So the free electron need to go, yeah, to make, yeah, the charge is uniformly distributed 是均匀分布的 on a outside a shell OK 只在球壳的地方 OK outside a shell not inside OK so the point here is that if we have another charge OK let's say this is this time we have a Q here can be also positive or negative I just maybe negative okay so in that case this part is negative this part is positive okay so you will assume that they will attract each other yeah but how large is the force okay if the total charge here is Q it will be the same as all the charge Q are concentrated at the center of this sphere and then with the same distance okay suppose the distance here is small r distance here is small r okay so for this case you can apply the Coulomb's law for this one you cannot because all the charge are distributed uniformly so you cannot count okay how many charges are there okay you cannot yeah definitely it's like an infinite number so you cannot add it up with a normal addition okay you need to use the integration to add infinite number together okay so here if it is like this this is one charge this is another charge okay so you can apply the Coulomb's law okay Coulomb's force is like F equals K times Q R squared okay and then it tells you that for the shell theory 1 it tells you that for this one the force here is actually equal to this one okay it's the same okay the shell theorem just tell you that like that okay so just like all the charges are concentrated at the center of the sphere and then the force will act on the sphere okay so you will say these two cases are equivalent to each other okay so this is what shell theorem tells you and yeah so for the shell theory 2 okay a charged particle inside a shell with charge uniformly distributed on the surface has no net force acting on it due to the shell okay so for the second case it will be like this okay not so perfect okay I try to draw less okay like this okay so you assume this is a perfect circle although I draw it not so perfectly yeah so so it says if you have a charge okay so still this is Q this is small q on the equally distributed or uniformly distributed on the surface and here you have a charge not outside this time inside no matter where it is the net force acting on the charge inside this sphere will be perfectly zero yeah so this is difficult to derive but if you have Gauss law then it will tell you because there were many of mathematics hide behind the Gauss law but we do not need to prove it because actually this is called a law what a law means is that you don't need to prove it for a theory you need to prove it for a law you don't need to prove it as long as the law can explain the correct phenomenon then it is correct unless you find a counterexample then you will say this law is not correct anymore but I guess the Coulomb's law has been exists, or this shell theorem has been exist for more than 100 years. So there are no counter example up to now. So I believe that it is correct. But anyway, I will not talk about the Gauss law yet because I will learn it in chapter 33. Anyway, shell theory 2 only tells you that a charged particle inside a shell with charge uniformly distributed on its surface has no net force acting on it due to the shell. Okay, so actually, of course, let's say for this part, this is positive charge, and let's say this is also a positive charge, so they will repel, and then for this part, they will also repel. So all the forces due to different part of the positive charge will perfectly cancel. Okay, the shell theory just tells you the point like this. Okay, all of the force, there are quite a lot of force acting on the charge, but all the force just cancel each other perfectly. So this case tells you that F equals 0, perfectly 0. Yeah. Okay, so this is checkpoint number 2. So the figure shows two protons. These PP are protons. This is electron E on an axis. On the central proton, what is the direction of the force due to the electron? Okay, force due to the electron. Okay, left or right? Central proton. Okay, left or right? The force acting on the proton due to the electron. Left or right? Left or right? No response. Left or right? Either is correct. Which one is correct? Okay, should be left. They attract each other, so left. And then the force due to the other proton, okay, also left. Yeah, because they repel each other. Okay, so the net force, okay, left, adding up to be left. Okay. Okay, so here comes a sample problem. So let's take a look at it. So it says figure A shows two positively charged particles fixed in place on an x-axis. Okay, so this is the x-axis. The charge are Q1. Okay, Q1 here, and then Q2 is here. Okay, Q1, Q2. And the particle separation is capital R. What are the magnitude and direction of the electrostatic force on particle 1 from particle 2? Yeah, so the force acting on Q1 due to Q2. Okay, so F12 will be K times Q1, Q2 over R squared. Okay, yeah. So so this is nothing but 8.99 times 10 to the 9th. Okay. Yeah, so and then Q1 is 1.6 times 10 to the negative 19, and then times 3.2 times 10 to the negative 19, all over 0.02 square. Okay, so during the computation steps, okay, you don't need to write the SI unit, but for the answer you need to write the SI unit. Okay, so use a calculator. You can know that this is 1.15. That's 1.15 times 10 to negative 24 Newton. Okay, 24 Newton. Okay, so this is the magnitude. Okay, what is the direction? Okay, of course you can say this is pointing to the left side. Okay, but if we try to write it as a vector form, F12 vector will be like negative 1.15 times 10 to negative 24 Newton I hat. Okay, so we'll use for the x-axis, wow, okay, z-axis, okay, we can use I hat, j hat, and k hat. Okay, actually not with a dot. Okay, so this is the unit vector for the Cartesian coordinate. For the Cartesian coordinate. Yeah, I hat, j hat, k hat. Usually we don't write the dot for the I and then the dot for the j. Okay, but sometimes I just write it. Okay, but in the textbook it won't have the dot there. Okay, it won't have the dot there. So it's like yeah, they used to be like that. Okay, so this is the this is that. Okay, so for the second one, okay, here we know F12 is like this. And then for this one, okay, we have another charged particle 3 placing somewhere between Q1 and Q2. And then Q3 is this value. And then at a distance 3/4 of r from particle 1. Okay, what is the net electrostatic force on the particle 1 due to 2 and 3? Okay, so actually we need to know the F12. Okay, so we don't need to calculate again from the previous question. So here what we need to know is F13, yeah, because we need to know the net force. So F13 will be like K times absolute value of Q1, Q3 over 3 over 4R quantity squared. Okay, so this is nothing but 8.99 times 10 to the 9th power, and then times Q1, what is Q1? 1.6. 1.6 times 10 to negative 19, and then this one, after taking the absolute value of 3.2 times 10 to negative 19 over 3 over 4, 0.02, and then the whole square, something like this. So which will be 2.05 times 10 to negative 24 Newton. Okay, so this is yeah, extremely easy, I think. So you can also write it as F13 vector will be, yeah, so this one, they will attract each other, so this force actually point to the right side. So this is 2.05 times 10 to negative 24 n I hat. Okay, so the F1 net will be F12 vector plus F13 vector. So which will be this one adding with this one. So it is negative 1.15 times 10 to negative 24. 24 plus 2.05 times 10 to negative 24. Yeah. So which is 9 times 10 to negative 25 Newton. Okay. Okay, actually I can also write it as n I hat. Okay, n I hat. Okay, I hat. Okay, will be like this. Okay. So this is the net force due to particle 2 and 3 acting on particle 1. Okay, so yeah, so the fourth case, yeah, so for question C, I mean, so here we have still Q1 and Q2, Q3 is removed, but here we have Q4 here. Q4 have the same charge amount as Q3, and then the distance is also the same, but with a 60-degree angle from the x-axis. So yeah, still we have a F12, and then the F14 should have a same magnitude as F13, but the angle is different. So here we can quickly know that F14 is yeah, actually the same value is 2.05 times 10 to negative 4 Newton, okay, as the previous one, and the F14 vector will be like two parts, 2.05 times 10 to negative 24 cosine of 60 degree Newton I hat plus 2.05 times 10 to negative 4 sine of 60 degree Newton J hat. Okay, so you need to decompose this F14 along the x-axis and also on the y-axis. So finally, F1 net in this case is by adding F12 with F14 together. So it will be negative 1.25 times 10 to negative 25 Newton I hat plus 1.78 times 10 to negative 24 Newton J hat. Yeah. So I don't think this is really difficult. You should have working on similar calculation during high school physics, not necessary for the charge, for the Coulomb's force. Yeah, but I'm very sure that you should have calculate similar stuff. Okay, so here let me talk about another sample problem. So this one says figure A. Okay, figure A shows two particles fixed in place. A particle of charge Q1 here, which is plus AQ at the origin, and a particle of Q2 negative 2Q. Here x equals L. At what point other than infinite far away can a proton be placed so that it is in equilibrium? Equilibrium means there is no net force, okay, acting on that charge. Okay, the net force is on it is 0. Okay, is that equilibrium stable or unstable? Okay, so this is a little bit off the topic. Okay, so this concept only exists on this sample problem, but nothing else. Okay, so just you can just try to understand it for this for this sample problem only. Okay, so before trying to do the calculation, let us try to do some interpretation. Okay, so where to put the charge? Okay, so if the charge is out of x-axis, it is impossible, because you can never cancel the y-axis component. So we only limit the possible solution to be on the x-axis. Okay, so actually these two charges separate the x-axis into three parts. Okay, so the left part, the middle part, and the right part. So let us try to consider each part individually. Okay, so the first case is if this positive charge, okay, it says the third one. Okay, the third one is a proton. The third one is a proton, so which means it is a positive charge, even though you don't know how large the charge is comparing to the AQ. Okay, you don't know. It does not give you the what value of the Q is. Okay, but you only know that it's a proton. Okay, so this is a positive charge. If it is this positive charge placing between Q1 and Q2, what will it be? So the left one, Q1 is positive. Okay, so positive, they will repel each other. They repel each other. And then Q2 is negative. So these two attract each other. So both forces pointing to the right side. So F1, F2 can never cancel each other. Okay, because they are pointing to the same direction. Okay, so we quickly discard this case. Okay, so for the second one, if the proton is placed on the left side, okay, so if you just consider the direction, okay, it may be okay. So because positive, they repel each other. So this one point to the left side, and then for the Q2, okay, negative, positive, okay, they are attracting each other. So this one point to the right side. Okay, so maybe possible, but if you go deeper, okay, it tells you that it is not possible. Because F is actually equal to K times, let's say Q1, Q2. I use capital letter here to skip this Q1, Q2, R square. Okay, it means that, so here Q1 here, Q1, okay, so this proton is fixed. Okay, so here we have a Q1 times the proton. Q1 is 8Q, okay, 8Q. So this is large. And then the distance, okay, is small. Okay, if you consider Q2 is only negative 2Q. Taking the absolute value is 2 compared to 8 is, much smaller. Okay, so for the denominator, it is numerator. I mean the numerator. The Coulomb's force for this one is much larger, and then for the denominator, okay, this is short, this is long. Okay, so which means that also this one is larger. So which means that F1 must be larger than F2, so they can cancel each other either. Okay, so we can also discard this case. Okay, so for the final one, okay, we must put the positive charge on the right side. Okay, so here it means that we already assume that x x should be larger than L. Okay, because we assume that the charge is placed on the right side. So here we have a K times HQ, 8Q times QP. Okay, so this is the charge of the proton. We don't know what it is, so we just use a symbol for that. And then if this one is x, so this is x squared. This one is x. Okay, so this one should be equal to k times 2q. We only consider the absolute value because we already know that, okay, the direction of f1, f2 must be opposite to each other. So we only consider the magnitude. So 2q times qp over, what is this? Okay, the distance from the proton to q2 is only x minus, okay, this one is L. Okay, so this part is x minus L squared. Yeah, so we can simply cancel this k, cancel this qp, cancel this q. Okay, we cancel many stuff. Cancel this 2 partially with this 8 to be a 4. Okay, so this is great. So we can just move this one to the left side, move this one to the right side. So we have 4x squared minus xl plus 4l squared equals x squared. Okay, so we have 3x squared minus 8xl plus 4l squared equals 0. And then this is a quadratic equation, so you have 2 solutions. One is x equals 2l, and the other one is x equals 2 over 3l. Okay, but we assume that x should be larger than l, so we just discard this one. So the only solution would be x equals 2l. X equals 2l. Okay, so whether it is stable or unstable, the idea is like f net should be, okay, f net should be k times should be k times 8q qp minus over something. Okay, over something. Okay, so this is already x. Okay, so the idea here is like if we try to put this slightly to the right side, like plus delta x. Okay, plus delta x. If we try to push it slightly to the right side, whether it will go back. So the idea here is like we have x plus delta x here, and then minus k times 2q qp over x minus l. X minus l is 2l. Yeah, 2l minus l is l. Sorry, should be. Let me see. Should be. Okay. This one should be. This one should be 2l. Okay, 2l plus delta x. Okay, this one is 2l delta 2l. Okay. So 2l minus l is l minus l plus delta x. L plus delta x. Okay, L plus delta x. Okay, because we already know that L is 2L. Okay, we try to put it slightly to the right side, which means that here x is actually 2L plus delta x. Okay, so put it to here, 2L plus delta x here, and then 2L plus delta x minus L will be L plus delta x. So we try to factorize it. So it could be like 2q qpk, and then we have a 4 over square here. We have a square. 2l plus delta x squared minus 1 over l plus delta x squared. Okay, something like this. Okay, so the question is whether this one is positive or negative. Okay, so if we just consider these parts, it could be like 1 over L squared plus L delta x plus delta x squared over 4 minus 1 over L squared plus 2L delta x plus delta x squared. Okay, here we assume that delta x is very small. Okay, delta x is very, very small, much less than 1. So which means that we can just simply ignore the last term. Okay, so we can easily feel that, okay, this one is smaller than that one, so this one is larger. Okay, so the first term is larger, which means that the whole forces, this one is larger than 0. Okay, this one is larger than 0. So which means that if this proton is slightly, we try to push this proton slightly to the right side, there will be a force acting on it, pointing to the right side. So we're further pushing to the right side. So this means that this one is unstable. Okay, it cannot go back. If it is stable, it should be able to go back. It's just like if you have a curve like this. Okay, you place a ball there, so the ball will roll back and forth, and then finally stuck at the lowest part. Okay, so this is why we will call this one is unstable.